Okay, thank you. Well, welcome everybody. Thank you for coming to our last seminar of the semester and of course of the spring 2017. It's a great pleasure to have today Dr. Baaziz Achour, who is the Senior VP at Qualcomm in engineering. And he joined Qualcomm in 1993 as an engineer and clearly has done very well since he climbed all the way to the very top. He also he worked as a system engineer in the CDMA for maybe some of you are too young to even remember all the steps that the digital communication had gone through. But at any rate, so he was really involved in the first launch of CDMA, the IS-95 and CDMA 2000. And in 2002, he joined the ASIC division of Qualcomm and to lead the system engineering and later the wireless modem technology. And so during his tenure at Qualcomm, he led the development of multiple technologies and successfully managed, of course, the delivery and the completion and delivery of various generations of modems, including CDMA, of course, WCDMA, TD-CDMA, GPS, and all the LTE generations. And now, of course, it's the 5G and probably very soon 6G or something like that. At any rate, you all know about the wireless revolution. Right now, basically, as far as I can tell, the wireless has taken over to the point where they're selling 800 million devices a year.
It's actually a quarter.
Say again?
It's a quarter.
Oh,
no, I thought it's a year. Oh, I mean 800 million, you said. A year, you're right. It's a year, sorry. Yeah.
And of course, they're in every phone that you guys own, the iPhone, all those things that you carry with you. And he graduated, of course, from Tufts University with an MS and PhD. He actually has a physics background, but had a good sense of steering back to it. And at any rate, he has a wide range of interests, including, of course, communication theory, cognitive radio. He's a theorist as well, so he actually can do hardware and the theory as well. So he's got many, many patents. It's a pleasure to have him here. Thank you for coming. The floor is yours.
Thanks, Dr. Akrim. Thank you very much. Thanks for the invite, and thanks everyone for coming. It's actually first time at NCSU, so thanks for all the reception. So what I thought to do is give you an overview on 5G. I'm sure you guys heard about 5G. LTE has been, a buzzword for the last 10 years. Now we're on to the next one, the 5G. And actually, listening to you, I feel really old now. And I might retire before 6G. So, okay. So I don't know how many of you know Qualcomm. I work for Qualcomm. So what I thought I maybe can share with you some high-level view of Qualcomm, so get an idea, and I'll give just a 5-minute overview. So basically, Qualcomm has two big businesses. One is this ASIC division where we sell chips to a lot of different industries, and mostly mobile space where all the phones that you guys carry, a lot of them have Qualcomm chipset in them. And a chipset has a lot of functions in it, and modem is just one of the pieces. So I'm responsible for the modem piece, but it's actually much more complex than that. People tend to talk a lot about modem, LTE, and all that, but actually there's a lot of cool technology in those chips. And the other division, which we refer to as QTL, which is our licensing business, basically a lot of the ideas that we come up with, that we patent, they're pooled into this portfolio of IP that Qualcomm actually licenses and charges for, and we make a really good margin doing that. So it's a pretty healthy business. This last quarter we made $6 billion revenue, and last year $24 billion roughly. So we're tracking to that, and we're basically the largest fabless company in the world, meaning that we design chips, but we don't fabricate them. We don't have factories. We actually send that to fabs like TSMC and Global Foundries and Samsung and a bunch of other companies that build the chip for us. We design the blueprint, and then once we get the chip back, we do the testing, the packaging, and we ship it to our customers. And then we add all the softwares, hundreds of millions of lines of code to make that work. We're about 30,000 employees. We're about 175 places around the world. We have an office right here in RTP. We do a lot of processor research and processor development here. We just announced that we're going to acquire a company called NXP. So by the end of the year, if everything goes well, we're going to be about 70,000 employees. So NXP is known for automotive space. They basically sell a lot of electronics in the car. All the entertainment, all the CPUs in the car, all the sensors, your tire sensor, all kind of things that go in the car, they pretty much have the leadership there. So the two companies combined, we're going to looking at a much, much broader company. So it changed from the days when, you know, it was just a few hundred of us. So the model for Qualcomm is really pretty simple. You know, we look for some challenging problems. We try to solve them. We try to solve them, and we patent those ideas, and then we share with our partners, and then we bring it to market, and we collaborate with, on the modem side, for example, we collaborate with the infrastructure vendors. These are the guys that build base stations to make sure, you know, it's a two-way communication, so we have to make sure we're talking to them, we're agreeing on all kind of things, plans and all that. And then we work with the guys that design the phones. We try to understand, you know, how to design an even more complex phone with all the different technologies that go into it. Radio, it's a tricky thing to design for. You know, you got a lot of different requirements, and I'll touch on some of those ideas in later slides. We also have an arm called Qualcomm Ventures. We actually invest in startups. And Qualcomm trying to basically invest in companies that basically expand the wireless space. But also it's an arm of Qualcomm that allows us to kind of know what's going on in the industry, kind of keep a pulse on the market, so we understand are we missing out on something and whether we need to, you know, maybe start something or invest in a company and such. So those kind of things that we have a corporate R&D group that's also in a lot of different places. There's actually a small group here in RTP as well. They do the research in the processor space, and actually have the locations listed here. RTP is on there, and it's basically the various area of research are kind of listed here. Just kind of high level. You can see deep learning in there. So we do have people looking at that space. It's a pretty exciting space now. Everybody wants to work in that space. There's a lot of wireless-related research, obviously. Typically, the corporate R&D team, they look out, 3 to 10 years, and they work closely with the ASIC division to make sure whatever they're looking at, we understand the constraint of that technology. So when it gets to a time where we need to implement it, we actually figured out a lot of the problems to solve, so we can bring it to market at reasonable cost, at low power, and high performance. So that's kind of in a nutshell, Qualcomm. And one last slide on Qualcomm is because the mobile space, the mobile is a very challenging environment to design for, because the phones are getting thinner and thinner and smaller. You don't have a lot of space for the electronics. And so to design a technology for the mobile space actually makes it very hard to design for low power, low cost, and high performance. So once you design a technology with that kind of constraints, basically that technology becomes very attractive to a lot of other industries. So now we're seeing a lot of interest from other segments of the market. So Qualcomm is going after the health space, and we actually have a small Qualcomm Health Services division. We're trying to grow that and trying to figure out how to manage the data in the hospital, how to connect all the instruments in the hospital. Of course, there's a wireless component of that, but also there's a data collection and fusion of data and all that, presenting that to the doctor when they have to analyze, for example, a patient. So there's some good, research going on there. Automotive, as I talked about, with NXP, we become a bigger presence in automotive. Over the last 15 years, we've been actually in the car as far as the communication aspect. So, we delivered modem in the car. Mostly the high-end cars, if you buy BMW or Mercedes or one of these high-end cars, most likely has a Qualcomm modem in it. With NXP, we're trying now to add all the other aspects of the car: entertainment, safety, pretty soon autonomous driving, and how we can improve on that. And so all these aspects kind of coming together, and it makes it very exciting as a new space for us to explore. Okay, so I got a lot of slides on 5G. What I thought, instead of diving in one particular topic, I thought I'm going to give you a broad view, so you guys know what's going on in the market, what kind of challenging problems we're trying to solve. There are a lot of views right now. You ask 10 people what 5G meant, probably you're going to get about 15 different answers. It's a lot of moving parts. There's a lot of hype, a lot of press releases, a lot of companies saying, you know, we're leading in 5G. But really, and I will talk about, you know, Qualcomm's vision in 5G and what kind of aspects have been already accepted in the standards body to actually pursue and try to come up with a spec that would enable 5G deployment. Of course, the last 30 years has been all about, you know, getting us all connected with our phones. Now, you know, the last estimate I saw was like 3.7 billion phones out there that are active. That's a lot of phones. And the next thing, you know, the next 30 years is, or 10 years for me, because I want to retire after 5G. It's going to be about, you know, all the things around us. So it's going to be, you know, everything that, you know, that needs to connect somehow to the internet needs to have a wireless connection. And wireless here means, you know, could mean anything. Could be 5G, could be Wi-Fi, could be Bluetooth, could be Zigbee, could be anything. So, but the idea is that it doesn't matter with the environment. There's always a connection to any endpoint in the, you know, in a network, whether it's a device or it's anything basically you can that has data to share with the world. So. Interestingly, like these Gs actually come every 10 years. It's kind of interesting how now the forecast for, I mean, you can really see the slide. I mean, basically, I started when the 2G was starting in the 90s, so that's where we were all trying to get voice to work. It was on GSM, and then, you know, we figured out a way. Qualcomm, that's actually Qualcomm kind of way. That's how Qualcomm grew and became big companies, because it found a way to deliver voice even much more effectively, a much higher capacity than GSM using CDMA, and that's where I had the fortunate, opportunity to work on that kind of problem, and we had to basically deploy CDMA, and we had to build it all at the time because people didn't believe in CDMA, so we had to build chips, we had to build phones. We actually had a phone division. We built phones. We sold, the stores. We built base stations. We built network planning tools. So I had to decide where to put the cell site so you have coverage in a given area. So pretty much done A to Z to launch CDMA. Once we saw interest, a lot of companies start investing in CDMA. Then we start pulling out of some of these areas. We pretty much sold our base station business to Ericsson, and we sold our handset division to Kyocera. And we decided to focus on IP, technology, and ASICs. And ASICs because you want a way to bring those ideas into the market, and you have to have a vehicle to do that. And once it goes out, then you have that leverage that your idea is in a product, so you can charge for it. So 5G. So like I said, now it's coming up, and it's really about three different things, and it's trying to allow all these different deployments, whether it's microcell, picocell, femtocells, mesh networks, relays, all these different topologies. We're trying to figure out a unified way, a network where it allows you to deploy in all these different conditions. It's also about spectrum. Right now, LTEs was designed for anything up, sub 3 gigahertz. But 5G is going to be looking at spectrum all the way to high 60 gigahertz in MiltoWave spectrum. Because in the sub 3 gigahertz, not much spectrum left. Spectrum is a finite resource. So we've got to figure out how we're going to better use spectrum, and I'll talk a bit more about that. This is actually a topic I want to spend a little bit more time on because it's actually a very scarce resource, and if we come up with some techniques that allow us to get more tracking efficiency and more use of that spectrum, then you can provide hopefully better service and also support many more devices out there. And then there is the services, and I'll talk about the services in a while. Basically, a lot of the networks were designed to support voice initially, and then internet access. And if you look at the different services that are emerging right now, there are things, for example, in mission control type of services where you want to control like a robot, you want to control a medical instrument, you want to control a lot of these very delay sensitive and very, you need a high reliability link to be able to actually make use of a wireless link. So those things are becoming an important aspect of where the industry is going, where the wireless industry is going. We're trying to cover all these new verticals. So it's an important design network that takes care of that. There are also these IoT, you heard about IoT, Internet of Everything. There's all these devices that now we need to have a wireless connection. And you can have billions of these things out there. And networks are not scaled to actually support all these little things that sit everywhere. They have a modem in them. That once in a while they wake up, they send a bunch of data, and they go back to sleep. And the design of the network actually was not done with that in mind. It was done with broadband in mind and deliver higher peak rates so you can browse the internet. That was kind of what drove a lot of the design of LTE. And 5G, basically, we're learning a lot from the things we did not do in 3G and 4G. We're trying to design from ground up a new network that would allow us to basically allow these services to coexist. And how can you basically optimize for different scenarios and different verticals in the market? So that's going to be an interest, a lot challenging from a network side and device side. So all these industries, pretty much you can divide this in three broad categories. There's the broadband, enhanced mobile broadband, which is basically the same, can LTE, but get even more bandwidth and low latency. There are interesting use cases coming up now. I'm sure you guys have a virtual reality or augmented reality. That requires a lot of bandwidth to make that really a good experience. There is a vision that pretty soon you won't have these phones. You just wear glasses that look just normal glasses, but they actually have you can see a screen in front of you, and it kind of superposes reality with the virtual reality. Or if you want to augment data on the stuff you're looking at, so that all requires a lot of data. And you have to kind of somehow make that bandwidth happen in low latency to the device. So all that a lot of these use cases are merging, and basically means we have to enhance on the broadband and make it even much more efficient. Then I talked about mission critical services. That's another category, and it has a lot of industries that kind of fall within that. And then the Internet of Things or everything, it's also, like I said, it's a zillion of things that need to be connected. So they have a different requirement than what the other two would have on the network. So they just kind of list some of these industries. There's just a sample. There's resource monitoring, whether it's agriculture, whether it's medical, whether there's all things that need to be taken care of. There's the cars, as we go into autonomous driving. It's a lot of cars need to now communicate to each other and communicate to the network, and there's all these reliability issues that come into play. So I have to make sure that we design the network to handle that. So if you just look at the requirements for each one of these segments, they a lot of places actually they're contradictory. So you can have for the Internet of Things, you have to have ultra low energy. The thing that the network or the design, the air interface has to be such that you can actually design a device that's very low cost, low power, that can maybe last 10 years on a battery. So that's a different requirement than designing something in a smartphone where you can consume a lot of bandwidth, a lot of data, because you have all these videos that you're playing or doing some other, doing VR or AR. So that's a kind of different, designing different parameters. And then you have mission critical stuff, which is also ultra low. If you have reliability, then you cannot have efficiency, because you're going to lose some spectral efficiency if you want reliability. It's all these contradicting requirements, and that's why 5G is struggling with trying to figure out how can I make sure that I cover all these aspects on the same network with some component technology that allows me to basically adapt my network to the demand of these services. If there's more IoT happening in the network, I can maybe move more resources towards that and configure them in a way that provides the most optimal QoS or quality of service for that particular segment. And if I'm doing broadband, more broadband, maybe I'll do something differently. So that's kind of some of the topics I'll touch on. I'll kind of show you just the kind of thing that Qualcomm identified as the challenging problems to go after, and I'll mention those in a while. So the ITU, the International Telecommunication Union, I think it stands for, basically they set a goal for the wireless industry. They said, we want these kind of improvements, and there's a kind of list at the bottom of the slide there. There's kind of actually like a very lofty goals. I mean, it's easy to say do 10x or 100x of something, but it's a big challenge for engineers that are working on these topics. And basically, the throughput today maybe on LTE, if you need good coverage, maybe you'll get, actually pretty soon we're shipping products that are shipping in the US this year. Pretty soon you can get peak rate of 1 gigabit per second on your phone. And so on average, maybe you get half of that, maybe 500 megabit per second on your phone. So we're already hitting the gigabits per second on LTE, and that's happening around the world, and it's probably going to be even more prevalent next year. So we're getting there with LTE, and with 5G, it's even, you want basically more bandwidth so you can afford and deliver that kind of bandwidth. Decrease in latency, LTE today, you can end-to-end, depending how you measure it and where you measure the endpoints, you're between 20 to 30 millisecond end-to-end. We want 5G to be sub 1 millisecond delay, so you can handle those mission critical services where, you don't want any delay, as you're controlling a robot or you're controlling, you know, a medical instrument remotely or things like that. So those kind of delays are required. And then you have the connection density. This goes to the number of devices it can handle in the network. So you have millions of these devices out there. You will make sure they don't overwhelm your network and you're able to manage them. And these are devices pretty much, you know, most of them duty cycle operation. They wake up, they do certain things, and they go back to sleep. Spectrum efficiency, 3x. Basically, you have to improve spectral efficiency. That's again, go back to the finite resource of spectrum. You know, you have to make sure we do better at using that resource because we're not gonna grow more of that. You know, it's fixed, and we have to figure out a way to use it. Traffic, that's the capacity. You know, how much traffic you can provide in a given unit area. And in 5G, basically, they're going to take advantage of the spatial direction or dimension and try to, you know, through beamforming and such, and trying to basically deliver even higher throughputs and therefore more traffic to a given area. That's something I'm going to spend a little bit of time on if I have more time. And then the energy, obviously, the networks, the way they operate today, they actually there are ways we can actually optimize for power and make sure that today, like we have all these broadcast channels that send down information about the system, and they pretty much blast this energy continuously at 43 dBm or something like that. And there are ways you can actually intelligent ways where you can get away from that and try to be maybe on demand request for information. And there are all these different protocols that could be used to allow for the basically trying to save energy. And same thing happens on the handset side too. There are other things that can be done to help. So this kind of summarizes basically the 5G kind of high level. You know, it's those three things: you know, deployment, services, diverse services that might not be all agreeing on the requirements, and then you have the spectrum. By the way, guys, feel free to stop me if you have questions or anything that's not clear. I'll skip this. I want to cover the other aspect. So actually, the work that's going on in 5G started many years ago. We actually had, even when we designed LTE, we knew there were a lot of things that were not really included in LTE because, you know, a lot of times market pressure, everybody wants to deploy something, and you tend to sometimes reduce your scope and cut corners in some cases. So, but we kept working on trying to figure out some of these other problems to solve. And the gigabit per second, you know, is the one we wanted to achieve on LTE. We're achieving that this year, but that comes, you know, it comes with some complexity on UE because it was not designed from ground up. You know, there are things that, you know, to support 4x4 MIMO, and then you have multiple carriers to deliver that kind of bandwidth for that kind of peak rate, puts a, you know, pre-taxing effort on the cost of the device. And these devices, you know, the price is pretty much kind of more or less fixed. It's really, you need to add more features, but always charge the same thing. So you have to kind of figure out a way to still make money for someone who's delivering chips in those phones. The 1000X challenge, this back in 2011, I think, there was a challenge. How would you address, you know, the data demand? You know, people start using videos. Everybody's watching YouTube on their phone. So the prediction was that in 10 years from 2011, we'll see the data basically multiply, you know, by 1,000 the demand. And basically, we have to figure out ways to address that. And actually, the demand is going up. It's kind of tracking to the 1000X if you keep track from 11 and on. And basically, it's a combination of, you know, better spectral efficiency, also using more spectrum and trying to find the spectrum that we could use. And and how to make use of technologies working together. For example, now we have these things where we could aggregate, you know, on the same session, you can aggregate Wi-Fi and LTE. So without you knowing, in the background, if we detect, you know, there's Wi-Fi locally and also there's an LTE network, we could actually make them work together so you can get the combination of both. It gives you a much better user experience. So that's one aspect that we look at. Actually, we're shipping in our products. Spectrum, you know, the wide area network world always worked in the same paradigm. You know, like, you know, a government assign a license, a spectrum license to a company, an operator like Verizon or AT&T, and they own that license in a given geographic area. And it's theirs. So when you go there, if you go on that channel, it's AT&T or it's Verizon. But there's a lot of unlicensed spectrum, you know, that sometimes people refer to as Wi-Fi, but it's actually Wi-Fi is just a technology that happens to be using that spectrum. It's not a Wi-Fi spectrum. But there are some restrictions how to use that spectrum. It's unlicensed, nobody owns it. You can just, through a CSMA protocol, you can just go in there and basically contend for the channel and use it for whatever service you want to build. Bluetooth uses that too, 2.4 gigahertz and 5 gigahertz. So the idea was that, why don't we have access to that spectrum as a one designer? So as a Verizon, for example, if some areas of their network, they don't have a lot of spectrum, and there's a lot of unlicensed, how can we make them, take advantage of the unlicensed, but at the same time, be friendly to Wi-Fi, because they're incumbent, so you have to make sure you're not coming, and step over Wi-Fi. So you have to kind of, you have to use the same protocol so you can, coexist with Wi-Fi on that spectrum, and then use that as an addition spectrum to the licensed spectrum. That's what's referred to LAA, which is license assisted access. Basically means that I can still be anchored on the licensed spectrum and talking to Verizon network, but I can add to that spectrum from the unlicensed and basically aggregate the two, end up with a much wider bandwidth spectrum, and therefore deliver much higher bandwidth throughput, and you get to hopefully have a better user experience. And then there's another paradigm in the whole spectrum. This whole spectrum use and sharing, all that is actually quite a whole research area how to figure out to make use of the spectrum. A third way that's been looked at, actually Qualcomm's been working with a few other companies. The idea is that instead of licensing a spectrum to a given operator in one area only to that company, you could potentially allow that spectrum to be used among maybe 2 or 3 companies and kind of get some tracking efficiency. And then you have to figure out then how to arbitrate between these operators and who uses when and all that. And in some cases, like in the 3.5 gigahertz, in some places in the US at least, the government uses that spectrum once in a while. So you have to figure out when they decide to use it, you want to get out of the way and let them use it and then come back use it. So all these things, there's actually even there's a DARPA competition to figure out how to design these kind of systems to actually arbitrate spectrum use. So that's a hot area. And then since 5G wants to basically expand across a span of spectrum all the way to the 60 gigahertz and up, even though there's a lot of talk about up to 40, but there's even ambitions to go above that, then having all these different ideas or ways to use the spectrum becomes very, very important. Connecting cars, now we have something called V2X, which is vehicle to anything, basically to infrastructure to another vehicle. And that's there's an IEEE spec called the SRC that also does the same thing, but it's less performing. Cellular world is developing this V2X basically to allow cars to communicate among themselves, and this is all building up to having better autonomous driving and also improving safety and all that. So there's a lot of that happening already in LTE, and we're building on that for 5G. Then Internet of Everything, obviously, like I said, it was not designed from ground up in LTE. It was added afterwards, so it's kind of costing, it's all signaling based, and signaling is taxing on the network. There's a lot of overhead and all that, and that creates a lot of burden on the network to even just support, some number of devices. This talks about, the spectrum again. It's basically all the way 600 megahertz all the way to, the high 50s, 60s gigahertz. And like I said, the three different ways of spectrum used in licensed, shared spectrum, and then unlicensed spectrum. So those are all ways that will come into the 5G. So as 5G happens, by the way, 5G is going to happen in multiple stages. It's not going to be just one spec and we have 5G. It's going to be, there's a lot of eagerness from a lot of the operators to claim they have 5G deployed. So in the standards body, where all the companies are haggling over the technical details of the air interface, or the network, and all these services, they're trying to figure out how to launch 5G. Because it's too expensive, and you cannot, by the way, if all the Gs before it, you can never deploy these technologies from kind of greenfield right away, and it's just too expensive. So what people will do, they're trying to build on top of what they already have. So meaning that Verizon will probably deploy a few cells in downtown Boston, and then claim that deployed 5G, but actually 98% of probably the time you're still on 4G. That's kind of, it happened on 3G to 4G. In Europe today, if you drive a lot of part of Europe, actually you're still on 3G, even though they have pockets of 4G, and then the phone says 4G, but actually that's not what you get most of the time. Because that costs a lot of money to deploy this overnight, so it takes years actually takes years to get to where you want. And in the meantime, you want the phone to be multimode, meaning that it can grab onto the latest G when it finds it, but as soon as the service, it goes out of coverage for that technology, you have a seamless transition or handoff to the older technology. And then similarly, the other direction, if you're in the old technology and you're driving into, let's say, a downtown area where 5G is deployed, you want to pick up 5G as quickly as possible. All that is left to the device to figure out, and that's part of the multi-mode. And also these other concepts called multiple connectivity, dual connectivity. For example, the phone can actually make two connections to different technologies so that basically you get a much more reliable link, and you can aggregate between the two of them, so you get a net result of a better user experience. And also allows you that, if you drive out of 5G, you drop into 4G or 3G or 2G. So that makes the multi-mode modem so complex because you pretty much have to handle all the transition between the Gs. You can go from 2G to 4G, 3G to 5G, and all these different transitions based on what the network actually is, what the device is seeing in the network. And that makes it actually, I think this is probably the most complex area of any modem development. There's a lot of innovation in the physical layer and the link kind of design. But really with the complication where a lot of the R&D is spent is actually in this area. It's really to make sure the phone can seamlessly go between all these Gs. And it only gets more complicated as we add 5G. So the other thing you would hear also is people talk about 5G NR. NR means new radio. They didn't really think too much to give it a name, so just new is a new radio. And then the other thing also people talk about sub-6 and MiltoWave. Basically in the spectrum, when you talk about 5G and about the spectrum for 5G, they talk about either about sub-6 gigahertz or everything above it. Basically, usually loosely, anything above 20 gigahertz they call MiltoWave, which is not quite exact, but kind of the people, the terminology they use. Basically, what I'm trying to say here for this one, it's not enough to get 5G working. We have to keep evolving LTE because, like I said, because of that continuity, you have to make sure that, if you drop from 5G to 4G, it's not a huge step function where you go from good service to very bad service. So if you make it, the step function is not as high. And that means LTE has to keep evolving, and it will happen. And so, like I said, gigabit per second was a big step, and we're adding a lot of other features that will make it. You may not deliver the same capacity, the same efficiencies as 5G, but you will be there to allow for continuity of service. These are some of the listed, some of the challenging areas that we're working on at Qualcomm, and we think that are worth solving, and they actually can make a big difference in addressing all these three major areas I talked about. In the massive IoT stuff, like I said today, a lot of the way the device comes on the network, they have to request a resource, and then they get a response, and then they get a grant, and there's all this back and forth. That's signaling. That takes time. That takes capacity. So there are other ways you can actually do with looking at ways to improve on that and actually have asynchronous access where you just burst energy and send a small packet, and that could be stepping on something that was already ongoing, and you have to have ways to recover from that puncturing that happens when that happens. So those kind of the type of things that be looked at. Also, there are things like how you design the waveform such that the device has time to go sleep and turn off all the hardware. So that's how you save battery, because you don't want to be staying on. And these things typically, requirements are you want to put a battery on it and leave it alone for 10 years, for example. If you're looking at, for example, a sensor that's monitoring, seismic activity on a bridge or something, you want to see if the bridge is moving or something, and you're going to put a sensor. They don't want to be replacing the battery every 2 days, so you want it to put it there, and then 10 years later come back and replace it maybe. On enhanced broadband, again, I talked about it's the same old for LTE, and we're just enhancing on that, improving the better spectral efficiency and all that through massive MIMO. Because of MiltoWave now, you could. It's a very short wavelength, so you could actually pack a lot of antenna elements in a small area, and you can create these arrays where you can give you a pretty good, you can do beamforming and get a lot of gain and get a better link budget and get better throughput. And then mission control, there are things also kind of how to efficiently multiplex these services. Latency is a big issue. So all these, I'll mention a couple of ideas that we're looking at that already been shared in the standard. One of these, by the way, is all this public information. So the other thing, before I forget, is actually if you go to Qualcomm website, we have actually a lot of documents, presentations, videos about 5G. If you guys are interested, someone interested to learn more, and you can download the presentations there, and you can yep. Yeah, sure, yeah, and I'll send it to Dr. Green. Yeah. Okay, so as far as the 5G design, so Qualcomm, obviously has again we try some of the companies actually like Ericsson, Nokia, and others are we're aligning on the same. We've been talking to among themselves for a few years now, agreeing on the concepts of LTE, of 5G, and we pretty much agree on these broad terms as far as what we need to go solve for 5G. Scalability, so we have to have scalability on both the time and frequency domain, and I'll talk about that. We have to have a framework where you can multiplex a lot of these services and have different requirements, and that's what's being looked at right now. And then there are things, improving, channel coding, and there is in LTE we use turbo codes. Here the slots or the TTI, time transmit intervals are shrinking and becoming very, very tiny. So you want an encoder and decoder that can actually execute very fast and get out of the way. You don't have the time budget is very, very constrained, and LDPC codes actually fit that bill for large packets. So LDPC code's been agreed that's going to be the channel coding we're going to be using 5G. For control channels, they're going to use different channel coding. They use Polo codes. So just it's not that much better than LPC, but because of the way standards work, sometimes you have to allow multiple options to get companies to contribute. So and then the guys that implement things, you have to decide which part to implement. So as makes it, you look at the spec, it's thousands and thousands of pages, and usually gives you 15 different ways to do the same thing, and you tend to basically figure out how to slice that and what part actually gets deployed in the real world. And the way that comes about is that we talk to a lot of the infrastructure vendors, the Ericsson, the Samsung, the Nokia, the world, the guys that design base stations. We also talk to the operators, the Verizon, AT&T, the big ones mostly, China Mobile in China, KT in Korea, KDDI or Docomo in Japan. And we try to understand what kind of things they're looking for, and then based on that, we narrow down the subset of the features, whether it's a physical layer feature or it's a network level feature. And that's how we come up with the actual what gets implemented and deployed. So that's actually a pretty long process. It takes a lot of meetings, sometimes it takes a lot of convincing, because we have to build a prototype, we have to show them the merit of certain features, why we want this to be deployed and not this other thing. And so usually the operators don't have a lot of R&D money to spend, so they rely on a lot of companies to do the R&D for them, and they triangulate basically, they listen to multiple, and then they make their own mind and what gets deployed. So we've been pretty successful actually at Qualcomm. We've been, pretty straightforward, and we're trying to figure out the best technology, because we know if you don't have the best technology, then the wireless may not go as well as we'd like, and our life depends on it. So we always push for the best technology, and then we try to show the pros and cons and let the operators and infrastructure hopefully come to a conclusion on the same terms. So OFDM is used in LTE. We use the spread spectrum in 3G. In OFDM, it's going to be used for 5G for multiple reasons. It scales much easier from an implementation perspective when you're doing high order, the MIMO scaling when you're going to 8x8 or 4x4 today. And so from implementation perspective, it's actually pretty friendly to implementation. It's less complex as opposed to we did MIMO with CDMA. It actually performed well, but it cost. It cost. The frequency localization, so you don't have the in-band and out-of-band emissions, so that's actually can handle that with OFDM. And then the other aspect that's important for the device is the peak-to-average power, and with OFDM you get actually pretty good peak-to-average PR that you could design for. And then you can do asynchronous multiplexing. It's the structure with the way the resources are structured with OFDM actually allows you to do this multiplexing of services. So that's why Qualcomm proposed OFDM, and everybody's on the same page. Actually, this is actually one of the items that was agreed to How am I doing on time, by the way? It's just 12:25 here. So.
You still have like 10, 15 minutes.
Okay. All right. Maybe I'll pick some slides that. Yeah. So this one here talks about the multiplexing aspect. So the other thing, also the other concept that's being looked at. So I think that if I can summarize what the bulk of 5G effort is going to be, I mean, there's all these exciting physical layer work needs to happen. You know, the LDP, even LDPC code has been used in Wi-Fi, but they're going to be used here. But there are some improvements you can make on LDPC code, delivery with better efficiency and better, from a implementation perspective, and better performance. So that work is ongoing from a lot of companies doing this work, including Qualcomm. There are things that, you know, the standard doesn't define how we do channel estimation, for example, or we do some filtering or whatnot. Those are all left to implementation, and they don't tell you. They just give you a spec. They give you a minimum performance spec you have to meet, and then it's up to the guys that build the modem to meet those specs. And we tend to be very involved. We want to make sure the specs, the performance specs, are set in a realistic way so that we can meet them. Because a lot of times they're based on simulations, and simulations doesn't capture everything. And you want to make sure that, you know, there are some things that you want to capture in those, the way the different thresholds are set in the standard so you can meet these specs when you have a device that needs to pass certification, for example. The other aspect that with this OFDM flexible platform is that you could actually leave certain resources blank from both frequency and time dimension. And the idea is that we don't know what we don't know today. We don't know what services might become, you know, hot in the future that could actually need to be supported efficiently in the network. So we want to allow for these blank resources so you can insert later on maybe a dedicated waveform that helps that particular thing that emerges years from now. So that's the kind of thing that was not there in LTE. In LTE, the parameters were fixed, and you actually kind of, with a lot of broadband support in mind. And so when we came in later to add IoT and to add all these other things, we made it work, but it was not the most efficient way to doing it. So in 5G, we're trying to think up, you know, ahead of time and see, okay, if there is something that comes up we don't know about today, how does this framework allow me to basically insert that service in an efficient manner when, you know, when I don't even know about it when I'm designing the network? So that's kind of the idea. It's easy said and done. There's a lot of, obviously, discussion and heated debates, you know, how to achieve that, and that's one of the things that that's being looked at. The other thing also that, you know, as you get wider in bandwidth, when you go to today, LTE was designed for different bandwidths, up to 20 megahertz component carrier, basically. You can have 1.4 megahertz, 5, 10, 15, and 20. And if you want more than 20, we go to something called carrier aggregation. Basically, we take a lot of these component carriers and we start aggregating them together. We can basically almost receive these different chunks of bandwidth separately, and then in baseband kind of combine them and create and get your throughput that way. That works fine, but it adds a lot of complication to a chip design. So as we do work on these standards, we have to think of ways to making a waveform that actually allows me to design a receiver that's not as complex. This way I can design things for much lower cost, also low cost and low complexity means low power, so I can, you know, enable other things that otherwise won't be possible. So as we go, one of the big things, you know, OFDM, obviously we have an FFT that has to work very hard to, you know, to process all these tones, and so as we go wider in bandwidth, you want to make sure that, you know, you keep in mind, you know, the complexity of that FFT, you know, and also the power that comes with it to, you know, to basically work on all these tones. And so basically the standard is going to, depending on the bandwidth that you get, you know, the tone, the subcarrier spacing, you know, basically has multiple configurations that handle that particular bandwidth. So in MiltoWave, they're looking at even having a bandwidth of 800 megahertz. Just imagine, you know, LTE is 20 is the largest you can get on component carriers. So 5G is going to be 800 megahertz. So that's how you're going to get in the gigabits per second, like 5 and above gigabits per second once done. So there are depending on the topology where you're deploying these things. You might just, you know, you have different bandwidth. You have 160 megahertz. You want to have certain spacing of the tones. Again, all to simplify some of the receiver on the UE side, on the device side. So that's one scalability that will be built into the network. there is this concept of TTIs. This is how you transmit these slots, how you transmit, and there are pros and cons of all different sizes of TTIs. In LTE, there's one size, and 5G they're coming up with different sizes. If you want high reliability, you have to go very small TTIs, but that costs spectral efficiency. And then also you have the configuration that allows you to pick larger TTIs, so you can get the spectral efficiency, but you lose reliability. But anyways, there are kind of things, the configurations that need to be put in place up front. So depending on the service you're trying to address or you're trying to support in the network, you could pick the right configuration that gives you the optimal user experience on the other end for that service. Another aspect, actually, this is stolen from Wi-Fi or borrowed from Wi-Fi. In LTE TDD, one thing we learned is that, like if you look at TDD, it's the same bandwidth. It's really either it's used downlink or used uplink. And the way the network are configured, they take the bandwidth and they say, 2/3 of the time is downlink and 1/3 of the time is uplink because the traffic is mostly downlink. So they kind of size it that way, and it's pretty static. Even though the traffic is changing up during the day and things might be, you're not actually using that spectrum efficiently because you kind of statically decided how you want to partition these things. So we're trying to change that, make it dynamic in 5G, and basically allow on a slot-by-slot basis to decide, if you contain everything within a slot, both the data and the act to that data, then you can basically get out of the way quickly, and you can, on a slot-by-slot basis, you can decide which one is downlink, which one is uplink. And that will, independent of the traffic pattern, it just adaptively, it adapts to the traffic during the day, and it gives you, therefore, a much more efficient way of using your spectrum. And also, it helps delay because you have a quick act, and it helps other aspects of deployment that I'm not going to talk a lot about here, but things like if you're dealing with in unlicensed spectrum, for example, if 5G goes in unlicensed, then you have a way to do the CSMA protocol. Basically, you sense the channel and then you decide when to grab the channel, then transmit, which is how Wi-Fi works today. I'm not going to say much about this. It's basically the LDPC improvement. There are something that I think it's something we call ME LDPC. It's basically an enhancement that we came up with on top of the LDPC codes that are used in Wi-Fi. And we think we can improve the performance as well, reduce the complexity so that, I have much smaller footprint of the hardware that needs to do that function, but also the less hardware. Also, if I clock it much lower the clock, then I get low power, and that again helps with the big picture of power consumption in the device, which becomes more and more challenging every year we release a new chipset because more and more functions are being added, and more things need to use the power in the battery. And if the modem can do a better job at the power, then these other things could take advantage of that power and hopefully, provide other services that don't exist today. Talk a little bit about IoT. Like I said, there was an afterthought in LTE. In IoT, now it's becoming hot, and a lot of people want to deploy, all these devices. And so what they did, they looked at LTE configuration. Like I said earlier, it was static configuration, and it was only this fixed bandwidth, 1.4, etc. And basically, they took the lowest bandwidth, which was 1.4 megahertz, and started using that for IoT, because that's all what's available in LTE. It's not the best from a cost and power perspective, but that's all the best you can get. And this feature called eMTC, machine type communication, which is basically the modem version or the modem configuration for IoT. And the E stands for enhanced. So that's basically what's getting deployed. Verizon is deploying this, and then a bunch of other operators are deploying this to service all their machines. And they want to add service where they charge a company, for example, to track your machines or track your fleet and whatever things that a company wants to track through these devices. And Verizon wants to offer that service. AT&T has a similar service. They use GSM, and they're going to phase out GSM, I think, in 2019. So they're looking at other technologies to replace it with. And narrowband IoT is another air interface that was designed to actually can go much smaller bandwidth, like sub 200 kilohertz. And that would fit. The reason it was designed that way because they want to reform the spectrum that GSM uses today, which is really small chunks of spectrum. Basically, they want to have technology that can be slotted in that spectrum. And narrowband IoT was basically devised for that. It's really a kind of parallel network. It's a separate network. It was not built in LTE, even though it uses the core network, the network side, but the air interface is actually separate on different channel. That's not efficient. You want it to be built in the network up front, and that's what 5G is trying to do basically. It's trying to take a lot of narrowband IoT concepts and basically slot them into that flexible framework I showed earlier, so you can allow narrowband IoT to coexist with all the other stuff we talked about, so they can have an efficient use of the network. This just talks about you need to communicate with all these different devices, and the last topic is really about talk a little bit about MiltoWave. Like I said, MiltoWave, because very short wavelength, you can pack a lot of antennas in a small area, and you can use that to create these beam forming, and you can actually use the spatial dimension to improve capacity and throughput. But it's a very complex thing to deal with, because MiltoWave spectrum hasn't been that attractive for many years. It's used only for line of sight. It's used for backhaul, used for for some limited applications like that. Using it in a mobile environment is actually a whole new thing. It's a lot of challenges, a lot of problems to solve. That's actually a rich area for a lot of problems to solve. And whether it's the base station side, how to design the PAs that would drive every one of those elements, or maybe do what they call a hybrid beamforming, which maybe you have a single transceiver drives multiple elements. It's all about, again, saving power at the base station. And the base stations have these massive antenna arrays, 256 maybe of elements, and you get more gain, and you get a better, beam direct link budget. And on the UE side, we have all kind of problems to solve. We have, you have to be able to design this. There's thermal issues. You have also, maybe you have 8 antennas, 16 antennas, these element antennas, and actually, starting with 60 gigahertz standard, the IEEE 11AD, which was published quite a few years ago. Now we start shipping products, actually. The very first time we start seeing active antenna used in the phones. It's the first time, actually. There's the first phone that's going to be shipped in June that's going to use 60 gigahertz for 11AD IEEE spec. And a lot of the use cases is actually for things like it's in a room environment, kind of, things like, for example, wireless docking. So basically, your phone becomes your laptop, and you have all the productivity software on your phone. As you get close to your desktop or desk, you only have a screen and a mouse and your keyboard, and it detects proximity, and then basically your Windows fires up on your screen. You don't have to have a laptop connected or anything. It's actually pretty common use case people talk about. And there are a bunch of other use cases that, also they talk about using that for virtual reality applications. There's a company in Utah called, I think The Verge. I think it's The Verge. What they do is they're trying to create this new business where they, it's a kind of game. You can play a game. You can pay some money. You go in this room. They give you a suit you wear. It's got a laptop at the back. And it's got all the rendering happening on the laptop, and of course it's weight, and it's processing, and it's got this HMD, the head-mounted display for your virtual reality. And you're in this world. It's an empty room, but you see this world. You have these guns, whatever you're holding, and you're playing games, and it's all real time. And but they want to get rid of all that weight behind you. They want to do it wirelessly. They want to have these access points in the room, and they want to deliver video and all that experience through wirelessly to the device, so you're much freer and have things where you weren't anything. They also want to do these multiplayer games, bigger room with maybe 10 users playing a game and going hiding and doing all kind of. I played with a couple of these, quite impressive actually. But the challenge with wireless there, it's quite interesting. If you're doing beamforming and you're trying to point it to a user, you're susceptible to blockage, you're susceptible to the reflections and all that. It's interesting problems to solve. And a lot of it is being, we learned quite a bit in this 60 gigahertz technology, and now a lot of that could be applied to MiltoWave. And what you see in the middle there is actually our prototype. We built a prototype. We actually implemented our version of MiltoWave 5G. We've done a lot of studies of how MiltoWave propagates, and can we really make it work in a mobile environment. And it turns out actually you can actually interesting reflections with MiltoWave. Like handrail like that could reflect. A pole could reflect. So trying to figure out how to make that work and it's not. The trick is that you can make sure you take advantage of this beam forming and get actually the data, but it's not always there. So it's going to constantly in and out for handoff, basically constantly handing up to another beam maybe, or handing up to another AP that has a different beam. So tracking and fast switching of beams and providing feedback to the AP, fast feedback to allow this to work. Those are all problems that need to be solved. And we have a solution for a lot of these things, and we're presenting our ideas in the standards, and hopefully we'll converse. And on the right side is a transceiver, 28 gigahertz transceiver that we put together. We're testing with. X50 is basically the name of the chip that we start shipping early next year. So like I said, smart beam forming and beam tracking, and then the other thing, you have to have a seamless handoff to a LTE or sub-6 5G, which is much more reliable from a coverage perspective. So you can, as you miss these beams or you get blocked, whatnot, you don't go zero throughput. You want to make sure you pick up by something else that's there. And it's not as good maybe, but at least it fills the gaps when you don't have the connection, you don't have a beam that closes the link. So those are all things that need to be, this whole beam forming and beam tracking and algorithm, how beam searching, how you select the beams, how you do a handoff, this is all ripe for a lot of innovation, a lot of work that could be, that will make a huge difference, people solving these problems. I think there's a lot we don't know today. There's a lot we're learning. I was very skeptical just a year and a half ago about MiltoWave. Actually, when we've seen all these demos we've done, all these trials, we're learning quite a bit. Actually, we made quite a progress. Now it looks like actually it could be very useful in mobile environment. So that's a big deal because that's the only place where you can find a lot of spectrum. The sub-6 stuff, it's all taken, or it's not a lot of. If it's available, it's not the big chunks of spectrum you're going to get. So this kind of shows just a few pictures of some of the trials we've done. We're trying to do a lot of trying to understand how the MiltoWave propagates. All these tests were done at 28 gigahertz. In the U.S., Verizon and AT&T have both 28 and 39 gigahertz, and in some markets they have 28, some markets they have 39. I think in some markets they have both. So we're trying to make sure whatever solution we come up with allows them to use one or the other, or both, or aggregate the two, and etc. to get wider bandwidth. I talked about this spectrum. The last topic, if I have another maybe 2 minutes or. Okay. The last topic is really about, it's been going on for a while actually. Now we're hoping that 5G will make it part of the strawman design and be done nicely and correctly. Again, after the fact with LTE, we realized that challenge with spectrum. We started thinking, how can we use unlicensed spectrum? So we had all these different initiatives. We had something called LTE-U, which is U for unlicensed. And we had this LAA thing implemented in the standard, license assisted access. And then we had this LWA, how can we make use of Wi-Fi and LTE at the same time so we can get the best of both worlds. And then there's 3.5 gigahertz work, this CBRS thing, I think it's Citizen Broadband Radio Service, I think. Basically 3.5 gigahertz, the government is trying to figure out how to share the spectrum. It's a licensed spectrum, how to make it, and also government also uses it sometimes in some places in the US. So that's the third paradigm I talked about, where you can share the licensed versus unlicensed versus licensed. So there are the different ways to use spectrum. So we did a lot of work in this area. We actually even decided to take LTE completely in unlicensed and basically compete with kind of Wi-Fi. Not that Wi-Fi is, nothing is going to beat Wi-Fi because it was designed with low cost in mind. So they gave up on performance to get the cost. So it's going to always exist. It's easy. You buy it, you plug it in, it's cheap, and it works. But there are a lot of spaces where you want something reliable. You want something that you can control, like all these industrial spaces where companies want to have their own private network. They don't want to depend on AT&T, on Verizon to manage their assets, because they don't want the data to get out of their network. They want a private network. They want to manage the network. They want a reliable air interface, and they want to make sure that they can tune it the way they want. And that basically brings in LTE. We said LTE has all those things, except it didn't have the unlicensed component. So basically, we designed an LTE with some modification outside the standards. We called it Multifire. There's actually a forum. You can go to look up Multifire forum. There's a spec, and we basically made some changes to the MAC layer to allow for the contention, channel sharing, where you basically just like Wi-Fi works. This way, if there is Wi-Fi in the area, we are friendly to Wi-Fi. We don't step on Wi-Fi, so we can all work, as happy colleagues. So I'm gonna skip this. So basically, in a nutshell, what Qualcomm does, we come up with, we're trying to design this air interfaces. We build our prototype. We test it. A lot of the ideas we help improve our proposal to the standards, and we go to 3GPP. That's the name of the standard body, and we make contributions. Of course, we make sure that we filed IP before we did that, so we have the patents. And then we do a lot of trials. We engage with these big machines, big FPGA boxes, and eventually we design what we call FFA, form factor accurate, which is small devices just like a phone that has our latest technology, and we use for trials and testing. We build thousands of those. We have a factory that builds for these phones, and we do a lot, so we understand the large-scale deployment of this technology, because you can't always figure out things through simulation. You have to kind of take it to the field and understand how things work. And then we build a chip eventually that goes into the iPhone, the Samsung Galaxy, and all these other phones that you guys you can buy. So lastly, the schedule for standards. So there's a mad rush now to finish the first version of 5G, and they're supposed to finish it by March 18. We're supposed to get a version of the spec by September this year, so that at least we know what's hardware impacting. So we're going to start working on the hardware. And then the software, the protocol will come later. So we'll see. But again, 5G is just the beginning. It's not like I said, one spec and it solves every problem that I talked about. It's going to be multiple phases. And the first phase, it's referred to as Release 15. And then we expect it to go for another 3 releases to really complete the picture and hopefully address all those challenges that I talked about earlier. That's pretty much the flyover 5G, and hopefully that was useful. Thanks for listening.